Welcome to this course about tools for data science. This course is designed for all learners who want to become data scientists. As a data scientist, you will be working with data, and this course will provide you with knowledge about various tools that you can use to analyze and derive conclusions. You can go through this course with or without programming knowledge. Now, a data scientist's toolkit consists of many tools, and in this course, you will explore a variety of them in the following modules. Module 1, Overview of Data Science Tools. Module 2, Languages of Data Science. Module 3, Libraries, APIs, Datasets, and Models. Module 4, Jupyter Project. Module 5, RStudio and GitHub. Module 6, Final Project, Create a Jupyter Notebook. And Module 7, an optional module, IBM Tools for Data Science. Let's now get some insight into what each module offers. In Module 1, you will learn about the different categories of data science tools and examples of open source and commercial offerings in each category. In addition, you will learn how the tools overlap in functionality and what their pros and cons are. Module 2 will give you an overview of the commonly used languages that are available in data science, like Python, R, Scala, Java, Julia, and SQL, and what they are used for. In the third module, you will learn about libraries that contain built-in modules providing different functionalities. You will also learn that an application programming interface, or API, allows communication between two pieces of software. Further, in the module, you will explore open datasets on the Data Asset Exchange, or DAX. And finally, you will learn how machine learning, or ML, uses algorithms, also known as models, to identify patterns in the data. In Module 4, you will learn about Project Jupyter, one of the most commonly used environments among data scientists. You will explore the three main applications of Project Jupyter, Jupyter Notebook, Jupyter Lab, and Jupyter Lite. In addition, you will be introduced to commercial Jupyter-based applications such as IBM Watson Studio and Google Colab. And this module also gives an overview of Jupyter distributions that can be installed on your own system, like Anaconda. Module 5 will start with an introduction to R and RStudio. You will learn about the different R visualization packages and how to create visual charts using the plot function. In addition, you will learn about GitHub, a popular version control platform that data scientists can use for sharing their projects and showcasing their portfolios. In Module 6, you will work on your final project, in which you will create and share your Jupyter Notebook. You will submit your project and also grade your peers. Finally, Module 7 is an optional module that gives an insight into additional IBM tools, like Watson Studio and IBM Cloud Pak for Data as a Service, that includes IBM Watson Knowledge Catalog, IBM Watson Machine Learning, and more. So there's a lot to cover here. To get the most from this course, complete viewing each video, complete all hands-on labs, and check your learning with each quiz. We are very happy to have you with us as you start your Tools for Data Science journey. And if you have any trouble with any of the course material, please don't hesitate to contact us in the discussion forum. So, let's get started, and good luck! Welcome to Categories of Data Science Tools. After watching this video, you will be able to list the tasks that a data scientist needs to perform, show how code asset management and data asset management help build models, and describe how execution and development environments implement a model. Before it can be useful, raw data must pass through various data science task categories such as data management, data integration and transformation, data visualization, model building, model deployment, and model monitoring and assessment. To do these tasks, you need data asset management, code asset management, execution environments, and development environments. Let's see how each category enables you to make the best use of raw data. Data management is the process of collecting, persisting, and retrieving data securely, efficiently, and cost-effectively. Data is collected from many sources like Twitter, Flipkart, media, sensors, and more. Store collected data in persistent storage so it is available whenever you need it. Data integration and transformation is the process of extracting, transforming, and loading data, and this is called ETL. Some of this data is distributed in multiple repositories, for example, a database, a data cube, and flat files. Use the extraction process to extract data from these numerous repositories and save to a central repository like a data warehouse. Data warehouses are primarily used to collect and store massive amounts of data for data analysis. Next, data transformation is the process of transforming the values, structure, and format of data. After extracting the data, the next step is to transform the data. In this example, height and weight data needs to be transformed to metric. And once the data is transformed, it's time to load the data. Transformed data is loaded back to the data warehouse. Data visualization is the graphical representation of data and information. You can use visualization to represent data in the form of charts, plots, maps, animations, etc. And data visualization conveys data more effectively for decision makers. It is a crucial step in the data science process. Various forms of data visualizations include a bar chart, which compares the size of each component, a tree map, which displays hierarchy data, a line chart, which plots a series of data points over time, and a map chart, which displays data by location. Map charts can also be applied to other locations, like websites. Now, model building is the next step. This is where you train the data and analyze patterns with machine learning algorithms. The system learns how to provide predictions or decisions by itself. You can then use this model to make predictions on new unseen data. Model building can be done using a service called IBM Watson Machine Learning. It provides a full range of tools and services for building models. The next step is model deployment, the process of integrating a developed model into a production environment. In model deployment, a machine learning model is made available to third-party applications via APIs. Business users can access and interact with the data through these third-party applications, and this helps them make data-based decisions. As an example, the SPSS collaboration and deployment services can be used to deploy any type of asset created by the SPSS software tools suite. Now, model monitoring and assessment run continuous quality checks to ensure a model's accuracy, fairness, and robustness. Model monitoring uses tools like Fiddler to track the performance of deployed models in a production environment. Model assessment uses evaluation metrics like the F1 score, true positive rate, or the sum of squared error to understand a model's performance. A well-known example is the IBM Watson Open Scale, which continuously monitors deployed machine learning and deep learning models. It will improve the accuracy and quality of your predictions. So now that we've reviewed the data science task categories, let's look at some of the tools that support them. Code Asset Management provides a unified view where you manage an inventory of assets. When you want to develop a model, you may need to update it, fix bugs, or improve code features incrementally. All of this requires version control. Developers use versioning to track and manage changes to a software project's code. And when working on a model, teams use a centralized repository where everyone can upload, edit, and manage the code files simultaneously. Collaboration allows diverse people to share and update the same project together. GitHub is a good example of a code asset management platform. It is web-based and provides sharing, collaboration, and access control features. So, as a data scientist, you want to properly store and organize all your images, videos, text, and other data in a central location. You also want control over who can access, edit, and manage your data. Data asset management, also called digital asset management, or DAM, is the organizing and managing of important data collected from different sources. DAM is performed on a DAM platform that allows versioning and collaboration. DAM platforms also support replication, backup, and access right management for the stored data. Development environments, also called Integrated Development Environments or IDEs, provide a workspace and tools to develop, implement, execute, test, and deploy source code. IDEs, like IBM Watson Studio, provide testing and simulation tools to emulate the real world, so you can see how your code will behave after it is deployed. An execution environment has libraries to compile the source code and system resources that execute and verify the code. Cloud-based execution environments are not tied to any specific hardware or software and offer tools like IBM Watson Studio for data pre-processing, model training, and deployment. And finally, fully integrated visual tools like IBM Watson Studio and IBM Cognos Dashboard Embedded cover all the previous tooling components and can be used to develop deep learning and machine learning models. In this video, you learned that the data science task categories are data management, data integration and transformation, data visualization, model building, model deployment, and model monitoring and assessment. And data science tasks are supported by data asset management, code asset management, execution environments, and development environments. Welcome to Open Source Tools for Data Science Part 1. After watching this video, you will be able to list the open source data management tools, list the open source data integration and transformation tools, list the data visualization tools, list the model tools for building, deployment, monitoring, and assessment, and list tools for code and data asset management. So, the most widely used open source data management tools are relational databases like MySQL and PostgreSQL. Also, there are no SQL databases like MongoDB, Apache CouchDB, and Apache Cassandra. In addition, there are file-based tools like Hadoop file system or cloud file systems like Ceph. You also have an Elasticsearch tool that stores text data, including the creation of a search index for fast document retrieval. Now, the task of data integration and transformation in the classic data warehousing world is to extract, transform, and load, or ETL. Data scientists often propose extract, load, transform, or ELT, as data is dumped somewhere and the data engineer or data scientist handles the transformation of the data. Another term for this process emerged: data refinery and cleansing. The most widely used open source data integration and transformation tools are the following: Apache Airflow, which was created by Airbnb originally; Kubeflow, which allows the execution of data science pipelines on top of Kubernetes; Apache Kafka, which originated from LinkedIn; Apache NiFi, which delivers a very nice visual editor; Apache Spark SQL lets you use ANSI SQL and scales up to compute clusters of thousands of nodes; and Node-RED also brings a visual editor. In addition, Node-RED is so low in resource consumption that it even runs on tiny devices like a Raspberry Pi. Now, let's discuss the most widely used open source data visualization tools. You must distinguish between programming libraries where you must use code or tools containing a user interface. PixieDust is also a library but has a user interface that facilitates plotting in Python. A similar approach uses Hue, which can create visualizations from SQL queries, whereas Kibana, a data exploration and visualization web application, is limited to Elasticsearch or data provider. And finally, Apache Superset is a data exploration and visualization web application. Model deployment is a crucial step. Once you've created a machine learning model capable of predicting some critical aspects of the future, you should make it consumable by other developers and turn it into an API. Apache Prediction I/O currently only supports Apache Spark ML models for deployment, but support for all libraries is on the roadmap. Seldon is an interesting product since it supports nearly every framework including TensorFlow, Apache Spark ML, R, and scikit-learn. Interestingly, it can run on top of Kubernetes and Red Hat OpenShift. Another way to deploy Spark ML models is mleap. And finally, TensorFlow can serve any TensorFlow model using the TensorFlow service. It can be an embedded device like a Raspberry Pi or smartphone using TensorFlow Lite and deployed to a web browser using TensorFlow.js. Model monitoring is an important step as well. Once you have deployed a machine learning model, you want to track its prediction performance while new data arrives to maintain outdated models. Some examples are the following. ModelDB is a machine model metadata base where information about the models is stored and queried. It natively supports Apache Spark ML pipelines and scikit-learn. A generic multi-purpose tool called Prometheus is widely used as well. Although it is not specifically made for machine learning model monitoring, it is used for this purpose. Model performance is measured by more than accuracy. Model bias against protected groups like gender or race is important as well. The IBM AI Fairness 360 open source toolkit detects and mitigates bias in machine learning models. These models, especially neural network-based deep learning models, can be subject to adversarial attacks where an attacker tries to mislead the model with manipulated data or by controlling it. The IBM Adversarial Robustness 360 toolbox detects vulnerability against adversarial attacks and leverages the model to be more robust. Finally, machine learning modes are often considered as a black box applying some magic. The IBM AI Explainability 360 toolkit addresses that problem by finding similar examples in a dataset to be presented to an end user for manual comparison. IBM AI Explainability 360 toolkit can also address the training of a simpler machine learning model to explain the responsibility of different input variables directed toward the final decision of the model. So the choice of code asset management tools has become quite simple. Git is now the de facto standard for code asset management, also known as version management or version control. Around Git emerged several services. The most prominent is GitHub, but the runner-up is GitLab, with the advantage that the platform is entirely open source and can be hosted and managed on your own. Another choice is Bitbucket. Data asset management, also known as data governance or data lineage, is a crucial part of enterprise-grade data science. Data has to be versioned and annotated with metadata. Apache Atlas is such a tool supporting this task. Another interesting project is ODPI Egeria, managed through the Linux Foundation. It is an open ecosystem offering a set of open APIs, types, and interchange protocols that metadata repositories use to share and exchange data. And finally, Kylo is an open source data management software platform with extensive support for data asset management tasks. In this video, you learned that data management tools are MySQL, PostgreSQL, MongoDB, Apache CouchDB, Apache Cassandra, Hadoop File System, Ceph, and Elasticsearch. Data integration and transformation tools are Apache Airflow, Kubeflow, Apache Kafka, Apache NiFi, Apache Spark SQL, and Node-RED. Data visualization tools are Pixie Dust, Q, Kibana, and Apache Superset. Model deployment tools are Apache Prediction.io, Seldon, Kubernetes, Red Hat OpenShift, mleap, TensorFlow Service, TensorFlow Lite, and TensorFlow.js. Model monitoring tools are ModelDB, Prometheus, IBM AI Fairness 360, IBM Adversarial Robustness 360 Toolbox, and IBM AI Explainability 360. Code asset management tools are Git, GitHub, GitLab, and Bitbucket. And finally, data asset management tools are Apache Atlas, ODPI Egeria, and Kylo. Welcome to Open Source Tools for Data Science, Part 2. After watching this video, you will be able to Compare and contrast different open source tools, and describe the relevant features of open source tools. Currently, the most famous development environment data scientists are using is Jupyter, which emerged as a tool for interactive Python programming. Jupyter now supports more than 100 different programming languages through kernels. This encapsulates the execution environment for different programming languages. A key property of Jupyter Notebooks is to unify documentation, code, output from code, shell commands, and visualizations in a single document. Jupyter Lab is the next version of Jupyter Notebooks, and in the long term will replace Jupyter Notebooks. The abundance of architectural changes makes Jupyter more modern and modular. From a user's perspective, the main difference between Jupyter Lab and Jupyter Notebooks is the ability to open different types of files, including Jupyter Notebooks, data, and terminals, and then arrange them on the canvas. Although it has been re-implemented from scratch, Apache Zeppelin was inspired by Jupyter Notebooks and provides a similar experience. Though one key differentiator is the integrated plotting capability. In Jupyter Notebooks, you are required to use external libraries in Zeppelin, and plotting doesn't require coding. You can also extend the capabilities by using additional libraries. RStudio is among the oldest development environments for statistics and data science. RStudio has its origins in the year 2011. It exclusively runs R and all its associated R libraries. In the R environment, Python development is possible. R is tightly integrated into the Jupyter tool and provides optimal user experience. RStudio unifies programming, execution, debugging, remote data access, data exploration, and visualization into one tool. Finally, Spider tries to mimic the behavior of RStudio to bring its functionality to the Python world. And although not on par with the functionality of RStudio, data scientists consider it as an alternative. In the Python world, Jupyter is used more. Now, this diagram shows that Spider integrates code, documentation, and visualizations, among others, into a single canvas. Sometimes your data doesn't fit into a single computer's storage or main memory capacity. Therefore, cluster execution environments exist. The extensively famous Apache Spark is among the most active Apache projects that are used across all industries, including many Fortune 500 companies. The key property of Apache Spark is linear scalability. This means that if you double the number of servers in a cluster, you roughly double its performance. Apache Flink was developed after Apache Spark continued to gain market share. The key difference between Apache Spark and Apache Flink is that Apache Spark is a batch data processing engine capable of processing vast amounts of data one by one or file by file, whereas Apache Flink is a stream processing image with its main focus on processing real-time data streams. And although both engines support both data processing paradigms at the same time, Apache Spark is the choice for most use cases. After Apache Spark and Apache Flink, Ray is one of the latest developments in the data science execution environments and has a clear focus on large-scale deep learning model training. Let's look at open source tools for data scientists, which are fully integrated and visual. This means no programming knowledge is necessary. The tools support a subset of important tasks that include data integration and transformation, data visualization, and model building. Now, Neem originated from the University of Constance in 2004. As you can see, Neem has a visual user interface with drag-and-drop capabilities. It has built-in visualization capabilities. In addition, it can be extended by programming in R and Python, and even has connectors to Apache Spark. Orange is another representative of this group of tools. It is less flexible than Neem, but is easier to use. In this video, you have learned about the most common tasks in data science and which open source tools are relevant. Welcome to Commercial Tools for Data Science. After watching this video, you will be able to list the commercial data management tools, list the commercial data integration and transformation tools, list the data visualization tools, list the model tools for building, deployment, monitoring, and assessment, and list tools for code assessment management, data asset management, development environment, and fully integrated visual. Let's revisit the overview of different tool categories. In data management, most of the enterprise's relevant data is stored in an Oracle database, in Microsoft SQL Server, or an IBM DB2. Although open-source databases are coming to the forefront, these three data management products are considered industry standard and will be around for a while. In addition, it's not only about functionality. Since data is the heart of every organization, commercial support availability plays a major role. Commercial supports are delivered directly from software vendors, influential partners, and support networks. Let's start with commercial data integration tools that comprise extract, transform, and load, or ETL tools. According to a Gartner Magic Quadrant, Informatica PowerCenter and IBM InfoSphere DataStage are the leaders. These are followed by SAP, Oracle, SAS, Talend, and Microsoft products. These tools support the design and deployment of ETL data processing pipelines through a graphical interface. They bring along connectors to most of the commercial and open source target information systems. Finally, Watson Studio Desktop includes a component called Data Refinery, which enables definition and execution of data integration processes in a spreadsheet style. In the commercial environment, data visualizations use business intelligence or BI tools. The focus of these tools is to create visual reports and live dashboards. The most prominent commercial representatives are Tableau, Microsoft Power BI, and IBM Cognos Analytics. Another type of visualization targets data scientists rather than end users. For example, the visualization can show relationships between different columns in a table. This functionality is contained in Watson Studio Desktop. If you want to build a machine learning model with a commercial tool, you should use a data mining product. The most prominent products in that space are SPSS Modeler and SAS Enterprise Miner. In addition, SPSS Modeler is also available in Watson Studio Desktop based on the tool's cloud version. Now, model deployment in commercial software is tightly integrated into the model building process. Here is an example of the SPSS collaboration and deployment services, which is used to deploy any type of asset created by the SPSS software tools suite. And the same holds for other vendors. Also, commercial software can export models in an open format. For example, SPSS Modeler supports exporting models as Predictive Model Markup Language, or PMML, which an abundance of other commercial and open software packages can read. Model monitoring is a very new discipline, and currently, relevant commercial tools are not available. Therefore, open source is the first choice. The same is true for code asset management. Open source with Git and GitHub is the de facto standard. Data asset management, often called data governance or data lineage, is a crucial part of enterprise-grade data science. Data must be versioned and annotated with metadata. Vendors, including Informatica Enterprise Data Governance and IBM, provides tools for these specific tasks. The Information Governance Catalog covers functions like a data dictionary, which facilitates the discovery of data assets. Each data asset is assigned to a data steward or the data owner. The data owner is responsible for that data asset and can be contacted. Then, data lineage is covered, allowing tracking back the transformation steps in creating the data assets. The data lineage also includes a reference to the actual source data. And rules and policies can be added to reflect complex regulatory and business requirements for data privacy and retention. Watson Studio is a fully integrated development environment for data scientists. Most people consume it through the cloud. And there is also a desktop version available. Watson Studio Desktop combines Jupyter notebooks with graphical tools to maximize the performance of data scientists. Watson Studio, together with Watson OpenScale, is a fully integrated tool covering the data science lifecycle involving all tasks discussed previously. They can be deployed in a local data center on top of Kubernetes or Red Hat OpenShift. And another example of a fully integrated commercial tool is H2O Driverless AI, which covers the complete data science lifecycle. In this video, you learned that commercial tools support the most common tasks in data science. Data management tools are Oracle Database, Microsoft SQL Server, and IBM DB2. Data integration tools are mainly provided by Informatica PowerCenter and IBM InfoSphere DataStage. These are followed by products from SAP, Oracle, SAS, Talend, Microsoft, and Watson Studio Desktop. Model building tools are SPSS Modeler and SAS Enterprise Miner. SPSS Modeler is also available in Watson Studio Desktop. Informatica and IBM provide data asset management tools. And finally, Watson Studio, together with Watson OpenScale, is a fully integrated tool covering the data science lifecycle. Welcome to Cloud-Based Tools for Data Science. After watching this video, you will be able to describe how commercial cloud tools support data science tasks, and explain how integration provides the ability to use the same tools for multiple tasks. Let's again look at the overview of different tool categories. Since cloud products are a newer species, they follow the trend of having multiple tasks integrated in tools. This integration is applicable for the tasks marked green in the diagram. So let's start with the fully integrated visual tools category. Since these tools introduce a component where large-scale execution of data science workflows happens in compute clusters, we have changed the title and added the word platform. These clusters are composed of multiple server machines transparently for the user in the background. Watson Studio and Watson OpenScale cover the complete development lifecycle for all data science, machine learning, and artificial intelligence or AI tasks. Another example is Microsoft Azure Machine Learning. It is also a full cloud-hosted offering supporting the complete development lifecycle of all data science, machine learning, and AI tasks. And finally, another example is H2O Driverless AI. Although it is a product you download and install, there exists a one-click deployment for the standard cloud service providers. Since the cloud provider does not do operations and maintenance, as with Watson Studio, OpenScale, and Azure Machine Learning, this delivery model should be distinct from platform or software as a service, or PaaS or SaaS. In data management, with some exception, software as a service or SaaS versions of existing open source and commercial tools exist. The cloud provider operates the tool for you in the cloud. For example, the cloud provider operates the product by backing up your data and configuring and installing updates. Some proprietary tools are only available from a single cloud provider. One example of such a service is Amazon Web Services DynamoDB, which is a NoSQL database. It allows storage and retrieving data in a key value or a document store format. The most prominent document data structure is JSON. Now, another flavor of such service is Cloudant, which is a database as a service offering, but in the background, it is based on the open source Apache CouchDB. The advantage is that complex operational tasks like updating, backup, restoring, and scaling are done by the cloud provider. However, the Cloudant service offering is compatible with CouchDB. Therefore, the application migrates to another CouchDB server without making any changes to the application. IBM offers DB2 as a service as well. It is an example of a commercial database made available as a SaaS offering in the cloud, taking away operational tasks from the user. Now let's discuss commercial data integration tools that include extract, transform, and load, or ETL tools, and extract, load, and transform, or ELT tools. It means the transformation steps are not done by a data integration team, but are pushed towards the domain of the data scientist or data engineer. Two commercial data integration tools widely used are Informatica Cloud Data Integration and IBM's Data Refinery. Data Refinery is part of IBM Watson Studio. It allows transforming large amounts of raw data into consumable, quality information in a spreadsheet-like user interface. So, the market for cloud data visualization tools is huge, and every major cloud vendor has one. An example of a smaller company offering a cloud-based data visualization tool is DataMeer. IBM offers its famous Cognos Business Intelligence Suite as a cloud solution. IBM Data Refinery also offers data exploration and visualization functionality in Watson Studio. Again, those are examples of a rapidly changing and growing commercial ecosystem among many established and emerging vendors. In Watson Studio, various visualizations depict data for better understanding. An example is this 3D bar chart that visualizes a target value on the vertical dimension that is dependent on two other values in the horizontal dimensions. And you can use colors to visualize the third dimension. Another data visualization is hierarchical edge bundling that depicts correlations and affiliations between entities. If sufficient, a classic bar chart can do the job as well. A 2D scatter plot with a heat map shows two dependent data fields on the y-axis with different color intensities. A tree map shows the distribution of subsets within a set. The famous pie chart does the same but in a non-hierarchical manner. And finally, a word cloud pops out significant terms in a document corpus. Now, model building can be done using a service. One example of a service is Watson Machine Learning. Watson Machine Learning can train and build models using various open-source libraries. Google has a similar service on their cloud called AI Platform Training, and every cloud provider has a solution for this task. Model deployment in commercial software is usually tightly integrated into the model building process. Here is an example of the SPSS collaboration and deployment services, which can be used to deploy any asset created by the SPSS software tool suite. And the same holds true for other vendors. In addition, commercial software can export models in an open format. For example, SPSS Modeler supports exporting models as Predictive Model Markup Language, or PMML, which other commercial and open software packages can read. In addition, Watson Machine Learning deploys a model that makes it available to consumers using a REST interface. Amazon SageMaker Model Monitor is an example of a cloud tool to monitor deployed machine learning and deep learning models continuously. Every major cloud provider has similar tooling. Another tool for model monitoring is Watson OpenScale. Everything marked in green can be done using Watson Studio and OpenScale. In this video, you learned that Watson Studio and Watson OpenScale cover the complete development lifecycle for all data science, machine learning, and AI tasks. In data management, with some exceptions, there exists a software as a service or SaaS version of existing open source and commercial tools. Two commercial data integration tools widely used are Informatica Cloud Data Integration and IBM's Data Refinery. An example of a cloud-based data visualization tool is DataMeer and IBM Cognos Business Intelligence Suite. Model building can be done using a service such as Watson Machine Learning. And Amazon SageMaker Model Monitor is an example of a cloud tool to monitor deployed machine learning and deep learning models continuously.